Data overload or hidden logic. In the last video, we finally solved the problem of seeing the gene network. With molecular sensors and micro-testing, we can nudge a single controller in a million people and watch the body release its tiny chemical signals in real time. Each micro-test gives us a massive molecular map, a readout of about 100,000 molecular counts, all captured as a long array of numbers. Only some of those molecules shift in response to the test. The rest stay at normal background levels. At 4 arrays per hour over several days, that becomes hundreds of arrays per microtest. Across the global pool, it grows into hundreds of millions of arrays. The output from these microtests might look like noise, but it isn't. Somewhere inside all this molecular data is the hidden logic we need to control our longevity genes. So now the question is this: can we really convert this raw molecular data into multi-layered gene control circuits? Mapping a controller's molecular signature. To begin this process, we first need a baseline. What does a normal molecular array from a breath test look like? As a person goes through their everyday routines, we collect thousands of breath samples. Those arrays become our baseline, a reference set that shows how each molecule typically rises and falls across time. Each position in the array traces its own baseline curve. Now imagine a single gene controller activated in just 1,000 cells of one person. Each breath test from that moment forward gives us another 100,000 value array, a snapshot of how many molecules of each type are leaving the body. Over hundreds of tests, every molecule class draws a second set of curves, the test curves. And when we subtract the baseline curves from the test curves, we see the net effect of the controller: a small upward shift, a downward shift, or no shift at all. In fact, most curves hardly move. Only a small fraction show consistent, meaningful changes. This same process is repeated across millions of microtests in the global pool. And from that enormous dataset, we uncover the precise pattern of molecular shifts this one controller can produce. Testing multi-controller combinations. Once we know the molecular signature of each useful single controller, we can move up one level in complexity. To fine-tune gene control, we need combinations. If one controller pushes a molecule too high and another pushes it slightly too low, then together they can bring the system closer to the target range. And because different controllers influence different molecules, there are endless possibilities for useful synergies. Every combination is tested the same way as a single controller. Compare the arrays, extract the deltas, and trace the curves across time. By repeating this process, we can identify combinations that produce clear, stable, and useful molecular patterns. Of course, you might be wondering, won't that be too many combinations to test? That's the challenge we explore in the next slide. Automating the evolutionary search. By this point, we've safely microtested thousands of promising controller combinations. But how did we do that without taking decades or bankrupting the entire system? Most of the work has to be done in silico. We let AI generate huge libraries of random controller designs automatically, built from what we learned in earlier rounds. AI filters out any designs that behave poorly, selects the promising candidates, and then hands those survivors off to the next round of microtests, and eventually, after many cycles, to full power testing for safety and efficacy. Every step of the loop, in silico generation, microtesting, and selection, is automated, creating a continuous evolutionary search. This approach turns an impossible design problem into a scalable discovery process. Instead of building the perfect controller one at a time, we let automation, mass production, and AI do the heavy lifting. And that's how we move from thousands of combinations to tens of thousands, quickly, safely, and at low cost. The individual tuning phase. Once the most effective controller packages have passed full power testing, we can finally return to the individual scale. The hard work is already done. We've mapped the behavior of thousands of controllers across millions of microtests, and we know which combinations are safe, stable, and reliable. At this stage, tuning becomes more focused. Each person's baseline molecular curves become the starting point, and the target is the youth baseline, recorded from the global pool of 20 to 25-year-olds. We repeat the same process as before, but now using only proven controllers. Small, low-risk microtests show which packages move an individual's molecular patterns toward those youth curves. Because the global discovery work is complete, the individual phase becomes far more manageable. The tools are proven, the youth baselines are mapped, and the risks are much lower. It isn't instant, but it's steady and practical. A data-driven way to guide each person's molecular profile back toward youthful patterns. The information systems advantage. Everything in this process comes from using the information systems approach described in Darwin's Machines 2024. Instead of trying to design perfect gene controllers by hand, we gather enormous amounts of data and organize it into clean information streams. In this case, molecular counts across time. Each stream becomes a signal that tightly constrains the problem set. When the map is detailed enough, we don't have to guess, and we don't have to understand every hidden pathway. We simply saturate the space with options, test how each one shifts the output streams, and record the results. The information itself tells us which controllers work, which ones fail, and which combinations reconstruct the network in useful ways. This replaces slow, expensive engineering with massively parallel discovery. The risk is distributed, the cost is low, and the process scales naturally. By treating gene control as an information problem, not a design problem, we can map the system with unprecedented resolution and finally guide biological systems by their signals, not by our assumptions.